In this lecture, we're going to talk about texture synthesis. First, we're going to review the gram matrix. The gram matrix G of a set of vectors V1 to Vn in an inner product space is the matrix of inner products. That means we take each pair of vectors and we form the inner product. Since there are n vectors, we have n times n possibilities to compute an inner product. However, there's some symmetry, so the gram matrix will obviously be symmetric. Let's look at one entry Gij of the gram matrix, that is the inner product of the vector Vi with the vector Vj. And again, the gram matrix is size n times n. Other names that are used are Gramian matrix or Gramian. G is symmetric, positive, and semi-definite. Symmetric should be clear because the inner product is symmetric, so it's commutative, and you can flip the order of the vectors and you still get the same result. Positive semi-definite will be clear later when we write the computation in a different way. The rank of G equals to the rank of X, where X is the data matrix, so that each row of X stores a vector-valued sample. That means we have n rows of the data matrix. Each vector is a row of the data matrix. Now, using this idea of the data matrix X, the gram matrix G can be computed as follows: G equals X times X transpose. And having a matrix of this form, the matrix has to be symmetric, positive, semi-definite, as you know from a linear algebra course. Finally, a set of vectors is linearly independent if and only if the gram determinant, which is the determinant of the gram matrix, is non-zero. We list this just for completeness. This is not something that we'll use for texture synthesis. I just would like to highlight two ideas that are really nice when we look at texture synthesis, and why texture synthesis is a good example, maybe for these two techniques in a broader context. So first, we can use backpropagation to modify an input image rather than the network weights. As we discussed before, one can compute the gradient with respect to any set of variables. So for example, if we have a neural network that we just abstract with a function f that takes an input image I and network weights w, then we can compute the gradient with respect to the input image I, rather than what we did before, where we had the same network function f, again that takes an input image I and the network parameters w, and here we computed the gradient with respect to w to train the network. But now what we have here is we compute the gradient with respect to the input image I. And we can then iteratively optimize the image pixels instead of the network weights. And we do that by changing the input image I and then adding or subtracting a step size times the gradient here. Another idea that we will see is that an existing network, for example the VGG network, can be used as feature extractor. This is very popular in machine learning applications itself, but it also can be really useful for applications such as texture synthesis and style transfer. The idea is that the different layers in the network output tensors, and then we can use these tensors directly or statistics extracted from these tensors to guide image synthesis algorithms. So what is texture synthesis? The idea is that you get an input image and you would like to create an output image that looks similar to the input image. So for example here, this one is an input image, and texture synthesis would give us this output image. The output image may or may not be larger or smaller than the input image, but very often people show the output image to be twice the size of the input image, and often people expect that a texture synthesis algorithm can produce output images that are larger than the input image. Here's another example of an input image that gives rise to this output image. We're not reviewing the discussion of what is a texture and what is an image. We'll just think of a texture as being some form of an image that has a lot of repetitive smaller features. For example, these radishes, and there are many, many radishes that are kind of all look similar in the sense that they're all radishes, or you have waves and they're all kind of smaller compared to the image size, and they all, in some sense, look similar. There are two papers. One is a really well-known paper that started this idea of texture synthesis using convolutional neural networks, or at least was one of the most foundational and famous papers in this area that was really early. And the second paper, this is the one that we'll actually discuss in more detail. It's just this second paper is a proper extension, so to say, of the first paper. So we'll just discuss the second paper. All right. So for the notation, let's look at this. We'll use I to denote the output image or output texture, also called target texture. And with I tilde, we denote the input texture, also called exemplar. Second, and for that, let's look at the image. We can, at the figure here, we can take a pre-trained network. Let's just say the VGG network, and this is more like an abstract representation of the VGG network rather than a precise depiction, where we have an image that can be fed into this network, and then there will be a bunch of convolutional layers. We'll not showing any activation functions or pooling layers, so they're just like convolutional layers, some other layers, and the image will be downsized, so the spatial resolution of the image will become smaller and smaller. Also, the number of channels increases more and more, where then at the end, finally, there are a few fully connected layers, and then we'll have a classification. So this is an image classification network. So when we feed such an image through the network, then after each convolutional layer, we have an output that is a rank 3 tensor of size, here C times width times height. So C is the number of channels, and width and height depicts the spatial resolution. So let's just say for now that there's a tensor that will be output after this convolutional layer, C4. And in the notation the paper uses, they use F superscript ln to denote the nth feature channel of the lth layer. So, for example, f superscript 4 and 3, that would denote the third channel that comes out of this convolutional layer C4. But then we also would like to have a way to denote the actual pixels within this tensor. And so for this, the authors have this Q, actually it should be a comma M, to denote the spatial coordinates of one particular scalar value. So F superscript Ln denotes a complete channel of size, width times height. And F superscript Ln subscript Qm denotes one particular scalar value inside the tensor that is output by layer 4. So while in the course I try to use C for the number of layers and width and height to denote the spatial dimensions, the paper actually go a different route. They would like to use N for the channels and Q and M for the width and height of the spatial resolution. So in the following, you will see that only a little of my notation and most slides use the notation of the paper. So now we see one of these tensors, and let's say we would like to compute a gram matrix from this tensor. Now we have a few choices. One, are we going to compute a gram matrix by computing inner products of channels? So we could say that we have C channels, and we could compute C times C inner products of channels. For example, we take the first channel, which would be this width times height image. So let's say the first channel would be this width times height image. And then we could compute the inner product of this width times height image with the last channel image. So let's say this one here. So this would give us one inner product. Or we can compute inner products of pixels that each have C dimensions. So for example, this pixel here would have these C dimensions, and we can compute the inner product between this pixel here with this pixel up here, for example, or this pixel up there. Each of these pixels has C dimensions. And here, the thing that the authors propose is to compute inner products between channels. So the gram matrix will be C times C for this type of tensor. Also, to compute the gram matrix, there's a choice of either computing it using inner products or outer products. For example, computing outer products of each pair of pixels and summing them up will be an alternative computation to computing inner products of each pair of channels. Again, something that you learn in linear algebra. I'll just mention it here in case you see different ways to compute it. All right, let's talk about how the gram matrix can be used to define a loss to optimize the output texture. So the idea was introduced by Gatys et al., but we're using the notation of the different paper to basically just write down and explain again what I explained before. So the gram matrix G is computed for each layer L that is chosen in the implementation. So it generally doesn't make sense to compute this gram matrix and gram loss for all layers in the network. We'll just choose a few layers, and you can refer to the paper of which layers the authors propose to choose. For one such layer L, the gram matrix will have size number of channels times number of channels depending on how many channels the output of this layer has. So each of these gram matrices that are extracted could have a different size. So the gram matrix of the nth layer has a scalar value denoted by subscript n prime, which gives the inner product of channel n with channel n prime. And for one inner product, as discussed, we need to iterate over each pixel position in the image, and we multiply the value of each pixel of layer n with the corresponding pixel in layer n prime. So that means that for each scalar value in the gram matrix, we have a sum over all possible pixel positions qm. That means we have as many elements in the sum as there are different pixels in the tensor. And so what you see here is really the multiplication of the value in one channel with the value in the other. So n and n prime denote the channels, everything else is the same. So qm are variables that run through the spatial resolution of one channel, or they're indexed the same way, so just indices that run through the spatial resolution. And q and m denote the actual spatial resolution, so q is the index that can maximally be q, and m is the index that can maximally be big N. Alright, and again, this is one scalar value. But there are actually two gram matrices involved in this texture synthesis. One, or not two types, so we have a lot of different gram matrices per layer, but we have two types for each layer. So one type comes from the input image or input texture, and the other comes from the output texture that we want to optimize for. So let's just look at this equation. This GLNN prime, these are the entries of the gram matrix that are from the output texture. And G tilde LNN prime, these are the scalar entries of the gram matrix of the input texture. And what you see here is an equation that gives you an energy for comparing these two gram matrices at layer L. And again, we do this at multiple different layers chosen in the implementation. But for one particular layer, we simply compute the differences and square them, and then we sum up over all entries in the gram matrices. So this is a very simple Frobenius norm squared. Or just think about it as taking the two gram matrices, building the difference gram matrix, and then squaring each entry. And then you sum all of them up. So the gram matrices at each layer can have a different size. And to normalize this somewhat, there is this term 1 divided by 2qm squared, so that the individual terms are better comparable. So this equation gives us one energy value for each of the chosen layers where we extract a gram matrix. And now we need to combine all these energy values somehow. So the total gram loss then simply sums over the individual energy values for the different chosen layers. And we can have a different weight for each of the different layers. Again, these very specific settings, you can look at the paper to see what suggestions the authors make for setting these weights. While we might not have all the relevant losses collected and described yet, we have enough to at least describe the outline of the algorithm. First, we load a pre-trained VGG network. Then, we take the input image I tilde and we make a feed-forward pass through this network. Then, we can extract tensors at the chosen layers and compute the gray matrices for each of the chosen layers. Also, we can initialize the output image or output texture I with random noise. Then we can define the gram loss as described before. And now we can use a process similar to training a network using a version of gradient descent. Again, we talked in optimization about multiple possible ways to use different optimizers. So here, same thing applies. You can pick whatever optimizer you like, and then iteratively refine the input image, input texture I, such that this gram loss is minimized. So in the original paper by Gatys et al., they proposed to use LBFGS, and this is one example where a more complicated optimization algorithm was used. And again, I think the reason is because optimizing the input image is easier than optimizing all the weights in a network. So it's also possible to extend this now, and this is what this paper, Deep Correlation something, proposes. And specifically, it suggests one loss that is similar to the gram loss, but just somewhat a complement to this gram loss, and then also two other losses to control the synthesis. So we'll discuss 3 more losses to augment the basic gram loss. So the gram matrix basically makes use of inter-feature correlations or inter-channel correlations. So we have correlation between feature maps FLN and FLN prime, where n is not the same as n prime. And now the authors propose to use something that measures intra-feature correlations. So correlations basically by a feature map with itself. So where that means these feature maps where n equals n prime. If you took some signal image processing course before, basically what the authors propose is to use a weighted autocorrelation. Before going into this formula, let's just give an intuition of what is computed. Basically, we have this thing here, FLNQM, which let's just say we have an entity which is one of these tensors coming out of layer L. And what we're doing is we'll look at one feature map, one channel at a time. So we think of extracting an image of size Q times M, where we have big Q times big M as defined before. So we have a grayscale image of size Q times N, M, and we have N of these grayscale images. And what we're doing is we do the computation for each of these N grayscale images separately. So what we're doing specifically is we compute the inner product between a grayscale image and a shifted copy of itself. So we will slide the one image copy over the other image copy, and we will compute the inner product, where whenever the pixels don't overlap, we'll assume that there's a 0 by padding the input, both of these image copies with zeros as required. Now, this autocorrelation just means we take correlation of one image with itself, and the correlation again is almost the same as the convolution except for the flip. So this is an operation you should be very familiar with already. So this is basically the same as what we learned in convolution and what convolutional layers do, except for now we do a form of convolution where the filter and the image are the same thing. So the filter is a copy of the image, and we're just doing convolution of a single channel. So we do convolution of a grayscale image with a grayscale filter. All right, so now this is one scalar output, and we get a scalar output for a particular layer L. That is one of the chosen layers L. And here we get one for each input channel N, and for each shift, that is relative shift ij, between the channel and the copy of the channel. So when we shift by 1 in the x and 1 in the y direction in this image or channel space, then we get one inner product. So we shift the channel over itself in the direction 1, 1, and then we get one inner product, and then this is the scalar value, that is the inner product. So when I and j are 0, the two copies are perfectly aligned with each other, and there are no pixels that are kind of sticking out to the side. There are no pixels where padding has to be active. The bigger or the smaller I and j get, the more the images are shifted with respect to each other, and the more pixels will basically have no corresponding pixel in the other copy of the channel. So the question is, how far out are we allowed to shift? So traditionally we can start by allowing a shift by half of the width and half of the height of the channel. And there's only one change to the regular correlation or regular autocorrelation. That is, there's a weight that is defined for each possible shift ij. So how will we compute this weight? The weight will simply be the number of pixels that overlap. All right, so here we only look at this. So this is basically the inverse of the number of pixels that overlap. Let's look at one example to make that clear. So for a single input texture, let the output of level L be this, okay, forget the 1, n times 5 times 5 tensor, with n being the number of feature maps in this layer L. So for each of the feature maps, we will compute the autocorrelation. So we will do n of these autocorrelations, and what we will do is we will now compute just the weight matrix, and we will do the inverse. So we will get nicer values, and we'll see how that is constructed. Let's just think of this as being the shape of one of the channels, and then the other copy of the channel is shifted over it. So how far are we allowed to shift? The idea is, with this shift being allowed half the width and half the height, you allow the shift to go as far so that the center of one shifted copy is not allowed to go outside of the boundary. So in the extreme case, maybe this 25 of the copy can be overlaid with this 9 here, or this 9 here, or this 9 here, or this 9 here. Let's just look at the extreme case. We think of a shifted 5 by 5 image overlaying this location here. Then what we would have is we would have 9 overlaying pixels. So out of the 25 pixels in the inner product, a lot of them overlay a 0. So we would get only 9, basically these 3 by 3 that overlap. So this value is 9. In the middle, if both of the feature maps perfectly align, there's ij is 0, there's no shift, then all 5 times 5 pixels will overlap, and so therefore this value 25. Now the exact weights are computed by taking the Hadamard inverse, which is simply the element-wise inverse. So this 9 will become a 1 divided by 9, and 25 will be 1 divided by 25. What this does, in fact, is it takes the autocorrelation and it weighs the boundaries higher. So this is lower, therefore the inverse is higher. What you notice in autocorrelation is a pattern that the middle values will be higher, and as you go towards the boundary, the values typically become lower. So one other idea is to allow shifts that are larger than what we initially allowed. You could allow shifts that are so large that only a single pixel overlaps, so that the top left pixel of one copy overlaps the bottom right pixel of the other copy. So only a single scalar value would overlap and would participate in the inner product. And this idea is used to enable the synthesis of larger textures that have a larger size than the input, because it creates somewhat this autocorrelation matrix of a larger size by allowing the shift to be more extreme. So let's look at, again, this example. We have a 5 by 5 channel. This is the spatial resolution is 5 by 5. And now, using these more extreme shifts, we can go to 9 by 9. Let's just look at this example. All right, so here in this extreme position, only a single pixel overlaps, and so in this position 2, and so on and so forth, and again with perfect overlap here in the middle, 25 pixels overlap. And this is an observation or proposition by the authors that this extension actually makes sense. Let's look at some example that they show. What you see here on the right is a brick texture and the corresponding extended autocorrelation, weighted autocorrelation, that looks like this. And so we would like to compare this to a brick texture that is really larger, but where we only compute the autocorrelation in a smaller region. Again, weighted autocorrelation. And so the idea is that this small texture provides, this thing here provides a pretty good guess how this one here looks like. It has a lot of similar features, and therefore it seems to be a good way to control the synthesis of larger textures. So how is then a loss derived from these autocorrelation matrices? Very similar to before, to compare two channels, these autocorrelation matrices are formed, and then again there's the difference, and squared. And so again, we sum overall pixels, we compute these differences, and we square. And now in addition, we basically sum overall channels. So we sum overall channels and all pixels. Finally, this is defined per layer again, and then we have the chance to give different weights to this loss per chosen layer. The paper also shows how to compute the derivative, but that is a minor detail that we're not gonna discuss in this lecture. So this is the equation of how to combine the different energy terms for the chosen layers. And so you see again there's this weight, which is a hyperparameter that can be chosen per layer. For details how to set this, we'll refer again to the paper. Let's look at some examples how this weighted autocorrelation that the authors propose compares to the regular autocorrelation. This is the input channel or grayscale image, and what you see here are multiple grayscale input images. And then in the second row you see the regular autocorrelation without the weights, and as discussed you can notice that these autocorrelation images become darker towards the boundary. The weighted autocorrelation proposed by the paper authors does not really show that the values get smaller towards the boundary. There seems to be more uniform colors, and so this might have, even though it's actually a very minor detail, it's just a weighting term, it is reasonable to argue that this can have some influence. It basically makes the values at the boundary more important. So here in these examples, you can see what this reweighting term, what the effect of this reweighting term is. Intuitively, maybe, let's look at the last column. You have this checkerboard pattern, and so here we see that this radial effect, how when you go closer to the boundary, the values get smaller, so it gets darker, dominates. But with this reweighting, one can actually see that there's a pattern that has the same periodicity as this original checkerboard pattern. A similar thing maybe can be observed here, and so the idea maybe is that this could be some intuition that this periodicity or this kind of repeated pattern can be encoded using these weighted autocorrelation matrices. So here's another loss proposed by the authors. They say that it is actually possible for the output image to look the same as the input image, which would be a trivial solution. Now, one could also ask for explicit enforcing of diversity of the results. This could be done by not looking at the actual statistics of these different tensors that are generated by a network such as VGG, but just by looking at the tensors directly. So for one particular chosen layer, we could compute this diversity energy. We sum over each pixel position qm and over each layer n. So we really take two rank 3 tensors, and then we form element-wise differences. So this is a scalar, this is a scalar. We form the difference, and then we square. Again, the diversity energies can be summed up over different layers, where for each layer there's this hyperparameter WL that allows one to weigh the different layers differently. one thing that the authors noticed is that the CNNs tend to produce checkerboard artifacts due to the unbalanced filters and strides. So a checkerboard artifact is something where the pixels are kind of light, dark, light, dark, light, dark, and they switch rapidly between light and dark in a, maybe almost per pixel it switches. So therefore, we're going to introduce a smoothness term to alleviate these artifacts. The idea of the smoothness term is to say that each pixel should be similar to its neighbor. But this is a particularly tricky loss that goes in this direction. If one would like that each pixel is similar to all four neighbors and puts a regular, let's say L2 loss on it, then the result might be too smooth. What the actual thing is that the authors want is they would like that each pixel is similar to at least one single neighbor. This can be achieved by something that's similar to this soft min. And we again see the idea of computing the exponential function of something, then operating there, and then taking the logarithm. So what we're doing is we'll take a pixel that has some layer L, channel N, and location ij, and this is something in the output, and we look at some neighboring pixel that is offset by only 1. So this delta I, delta j can be plus minus 1. So we look at one pixel either to the top, to the left, to the right, or to the bottom. So it's a 4 neighborhood that we're considering here. So we compute the squared differences to the 4 neighbors, then we multiply by minus sigma, where sigma is a hyperparameter. The authors suggest 1e minus 3, and then we take e to the power of, and then there's an important factor 1 divided by 4. So and then the whole thing will compute the logarithm, and that's basically it. Okay, so we have an energy that is computed for a particular layer L, and that's the smoothness energy. And so what we do is we sum over each pixel, that is over each spatial position I and j, and over each channel N, and for that particular pixel and channel, we compute this elaborate difference to the 4 neighbors. And this difference is computed in such a manner that if the pixel has at least one similar neighbor, this will be a low value, but if all 4 neighbors are different, then this will be a higher value. This definition of loss actually makes sense for the actual output texture as well as any intermediate tensors that are output after a VGG pre-computed network layer when the output texture is fed through the VGG network again. Just a note that the paper is missing this 1 divided by 4 term. The idea is that let's assume that the differences to all 4 neighbors are 0. Then we would get e to the power of 0 plus e to the power of 0 plus e to the power of 0 plus e to the power of 0 for the differences to the 4 neighbors. And this would be 4. And so we need to divide by or multiply by 1/4 to get a 1, and then we get the logarithm of 1 is 0. So if the pixel has the neighbors all the same, then this term will be 0. You need to be careful because you have to do proper boundary handling. So if your pixel is at the boundary of the image, you need to find a way to slightly adapt this equation. Also, as with all the other losses, this smoothness term can be defined for different, can be weighted differently for the different layers. So we discussed 4 different losses. So the final energy or final loss is a weighted combination of the Gram loss, the deep correlation loss using this weighted autocorrelation, the diversity loss, and the smoothness loss. The authors suggest these weights to weigh these 4 different loss functions. Now, diversity needs to have a negative value in order to maximize the difference of the feature values. Also, this gamma weighing the smoothness term needs to be negative because this behaves in such a way that it becomes smaller with bigger differences between adjacent neighbors. Let's look at some examples. For example, this input here gives rise to this output, and this looks very good. Also, this texture here, the output looks very good. Most of the time, one needs to zoom in to really see something and to see artifacts. For example, the brick wall, maybe this is a bit too wobbly down here, or other locations. I guess one would also need to check if all the brick separations are okay. Again, maybe, I don't know, this is a bit wobbly. This might not be represented in the input. But overall, these results are of very high quality. Some more results on more stochastic textures, and again, they look really good. Again, you would need to zoom in and study the results more carefully to see where the textures, the output textures, have artifacts. This is an ablation study of using only the Gram matrix loss or only the deep correlation loss. Column A is the input texture. Column B uses the Gram loss only, and column C uses the deep correlation or the weighted autocorrelation loss only. Still together with the other terms, I assume. And D is the output using the complete combination of both losses, the loss in B and the loss in C. Now, this is an example where the difference is quite subtle. The paper shows other examples where the difference is a bit bigger, and some where it is substantial. Still, this gives some indication that one has to do quite some work in parameter tuning to get good results, and also that for some textures a very simple model will give almost the same results. Alright, this concludes the presentation of this paper, and I hope you have fun implementing it and that you can get also some very good